Welcome to the Cognito Pod.
Great to be here.
Today we're doing a deep dive into rare earth elements. You know, those 17 metals that are just essential for so much modern stuff.
Absolutely. Smartphones, clean energy like wind turbines, even high-tech defense systems, they're everywhere, really.
And the market's already big, right? Something like $5.6 billion now.
Yeah, and projected to hit over $10 billion by 2030, so growing fast.
But here's the kicker, the main challenge we want to unpack today.
The concentration. One country, China, basically controls, 70% of the actual mining?
Exactly. And even more of the processing, somewhere between 85 and 91%.
Which is why you're seeing this global scramble, this race to build up independent supply chains.
So in this deep dive, we'll cover what they are, where we find them, why they're such a big deal.
We'll look at the major companies involved, the countries competing.
And why they're competing, plus the challenges and what the future might hold.
It's pretty critical stuff. Imagine a world where, EV production just stops.
Or wind turbines fail, missiles don't work. All because of minerals you've probably never heard of.
That really underlines their importance, their hidden power.
Okay, so let's start with the basics. What exactly are rare earth elements?
Well, technically, they're a group of 17 metallic elements. You've got the 15 lanthanides on the periodic table, plus scandium and yttrium. Now, scandium and yttrium aren't lanthanides, chemically speaking.
Right.
But they tend to show up in the same mineral deposits and behave similarly, so they get lumped in.
And it helps to split them up further, doesn't it, into light and heavy?
Definitely. You have the light rare earths, or LREs, I think cerium, neodymium, and then the heavy ones, the HREs, like dysprosium and terbium.
And there's a big difference in cost and how common they are.
Oh, absolutely. The heavy ones are generally much scarcer and way more expensive. Dysprosium, for example, might run you $300 to $500 a kilogram.
Wow. Compared to
cerium, a light one, which might only be, say, $5 to $10 per kilo. Big difference.
Now, about that name, rare earth, it's a bit misleading, isn't it?
It really is. Geologically, many of them aren't rare at all. Cerium, for instance, is actually more abundant in the Earth's crust than copper.
So plenty of it around, just not concentrated.
Exactly.
Yeah.
The rarity isn't in the existence. It's finding deposits where they're concentrated enough to make mining economically feasible. That's the tough part.
Like finding gold dust spread thinly in a giant sandbox, maybe.
That's a good analogy. Finding it is one thing, but then separating these elements from each other because they're chemically so similar, that's a whole other challenge. It's complex, energy-hungry, and expensive.
And what are their key properties? What makes them useful?
They're typically silvery white metals, quite soft and reactive. But the really important properties are their unique magnetic and conductive capabilities.
Like neodymium magnets.
Precisely. Those little magnets can be incredibly powerful for their size, maybe 10 times stronger than standard iron magnets. That magnetic strength is crucial for a lot of applications.
Okay, so where do we actually dig them up? What kind of minerals?
The main sources are minerals, like bastnasite. That's the primary one at Mountain Pass in the U.S. Then there's monazite, found in places like India and Australia.
And China has those ion adsorption clays.
Yes, particularly important, because they tend to be richer in the valuable heavy rare earths. But there's a complication.
The radioactivity?
Right. These ores often contain radioactive elements like thorium or uranium. That makes extraction and dealing with the waste much more complex and hazardous.
Just to get a sense of scale, how much is out there versus how much we mine?
The U.S. Geological Survey estimates global reserves are around 130 million metric tons of rare earth oxide equivalent.
Okay, quite a lot.
But in 2024, the total amount mined globally was only about 390,000 metric tons.
So less than, 0.3% of the known reserves were extracted last year?
Exactly. It just highlights how difficult and intensive the whole process is.
And we see the results everywhere, like the tiny magnets in your smartphone speaker.
Made with neodymium, crucial for sound.
Or dysprosium in wind turbine magnets, helping them work efficiently even when they get hot.
Everyday examples of things we take for granted, powered by these elements most people never think about.
Okay, let's shift to geography. Where are these reserves and production actually located? You said they're scattered, but a few places dominate.
That's right. Looking at reserves, based on USGS data from 2023, China is way out in front. They hold about 44 million metric tons.
Which is about a third of the global total?
Roughly 33.8%, yeah. Key areas are Jiangxi, Inner Mongolia, and Sichuan, especially Sichuan, for those heavy rare earth clays.
Who's next?
Vietnam has the second largest estimated reserves, around 22 million metric tons, or nearly 17% of the total. Mostly in the Northwest.
And is that being developed?
Some, but interestingly, a lot of the processing of Vietnamese ore is actually done by Chinese firms right now.
Okay, and Brazil?
Brazil's third, with about 21 million tons, just over 16%. They have a promising ionic clay deposit called Pela-Ima, focused on magnet materials.
Then Russia?
Russia has about 10 million tons, maybe 7.7%, mostly Kola Peninsula, Siberia, but their actual production hasn't really matched those reserves historically.
What about India and Australia?
India has around 6.9 million tons, over 5%, mainly in coastal sands, but their output is pretty minimal. Australia's got about 5.7 million tons, around 4.4%, with Mount Weld in WA being a key site.
And the U.S.? We hear about Mountain Pass.
Yep. The U.S. has about 1.8 million tons in reserves, roughly 1.4% globally, with Mountain Pass in California being the main operation.
Greenland, too, right? There was talk about that.
Yeah, Greenland has estimates around 1.5 million tons, about 1.2%, mostly in the Gardar province. Definitely attracted Western interest for diversification.
And the rest is spread out.
The remaining 16 million tons or so are in various other places. Kazakhstan sometimes gets mentioned with potentially large deposits, South Africa, Canada.
Okay, so that's reserves. What about actual production in, say, 2024? Still China leading?
Oh, definitely. China produced about 240,000 metric tons last year. That's around 61.5% of the global total.
Which is down from previous years, though.
It is. It was up over 80% back in 2016. Quotas and environmental crackdowns have brought it down somewhat. But importantly, they also imported a lot, like 38,000 tons from Myanmar.
Myanmar, so they're producing quite a bit too.
They're third, actually, with around 38,000 tons, almost 10% of global production. But nearly all of it goes straight to China, and there are major environmental concerns about how it's mined there.
Who's second in production then?
The United States. About 43,000 tons in 2024, around 11% of global output, all from Mountain Pass. Supplies maybe 15% of global demand.
But we still send the concentrates to China for refining, right?
That's been the case, yes. Though MP Materials is starting its own separation now.
Okay. Australia.
Australia produced around 18,000 tons, about 4.6%. Mount Weld is the source. They're a really important non-Chinese supplier.
And Thailand. You mentioned a big jump there.
Yeah, Thailand hit 13,000 tons, over 3%, which is a massive increase from 2023, apparently due to new investments.
Anyone else significant?
Well, Brazil's output was tiny in 2024, like 20 tons,
Hmm.
but they have plans to scale up the Pela-Ima project to 5,000 tons by 2026. Nigeria also signed an MOU with France, hinting at future potential. India's production is negligible right now.
So pulling that together, China's dominance is clear, helped by state control and historically looser regulations.
Right. The U.S. is boosting mining, but has that processing gap it's trying to fill.
And places like Brazil and Vietnam have potential but need investment and development.
Exactly. And then you have challenges like the Arctic conditions in Greenland or infrastructure needs in places like Kazakhstan.
Plus, there's this looming gap between current production, even at 390,000 tons.
And what might be needed in the future. The IEA talks about needing maybe 1 million tons a year by 2040 for clean energy goals. We're nowhere near that.
It really paints a picture. You've got this high-tech facility at Mountain Pass on one hand.
And then these largely unregulated, environmentally damaging mines in Myanmar on the other. Geography, power, sustainability, it's all intertwined.
Which brings us to the core question. Why are these elements such a big deal? What makes them so critical?
Well, you called them unsung heroes earlier, and that's pretty accurate. They're fundamental to so much modern tech, green energy, and defense because of those unique properties. Magnetic, conductive, resistant to corrosion.
Let's break down the applications. Technology first.
Okay, so in your smartphone or laptop, you've got neodymium magnets in the speakers and hard drive motors. It might only be half a gram per phone.
But multiply that by billions of phones and it adds up fast.
Exactly. Plus, elements like lanthanum and cerium are used in semiconductor manufacturing to improve chip performance. Vital for things like AI and 5G.
And clean energy. That seems to be a huge driver.
Massive. Electric vehicles are a prime example. The motors use neodymium and dysprosium magnets, maybe around 1 kilogram per typical EV motor.
And with EV demand projected to soar?
Right. The IEA thinks we might need 100,000 metric tons of rare earths just for EVs globally by 2030.
Wow. What about wind turbines?
Even bigger quantities per unit. A large offshore wind turbine can use something like 500 kilograms of rare earth magnets.
500 kilos per turbine.
Yep. So if the U.S. built out its planned offshore wind capacity, that alone needs thousands and thousands of tons. They're also used to improve efficiency in batteries, both for EVs and grid storage.
And defense is another critical area.
Absolutely. Neodymium magnets are in missile guidance systems. Yttrium is used in advanced radar and sonar. Gadolinium in MRI tech, which has military applications.
I read a Virginia-class submarine uses tons of these magnets.
It does. And elements like erbium and holmium are key for high-performance lasers used in military optics. Even medical imaging relies on europium and cerium, making up a decent chunk of demand.
So the economic side is clearly significant too. That $5.6 billion market growing to $10.4 billion.
Driven largely by EVs and renewables, but it's not always smooth. The saline price volatility is a real issue.
Like when neodymium prices spiked.
Yeah, neodymium oxide jumped from maybe 50 kilograms in 2020 to over 150 kilograms in 2022, partly due to China's actions. That can add, $1,000 or $2 to the cost of an EV.
And the U.S. is heavily reliant on imports.
Still imports a lot, around $170 million worth in 2024, and something like 80% of that comes from China. That highlights the economic vulnerability.
Which leads straight into the geopolitical stakes.
Which are incredibly high. China's controls 70% of production, 91% of processing, and dominating permanent magnet production at around 94%.
That gives them huge leverage, doesn't it? Like that 2010 export ban to Japan.
Exactly. Prices spiked tenfold. It showed the world how dependent it was. This vulnerability is a major concern for Western governments, especially the defense sector.
The U.S. Department of Defense relies on Chinese REEs for things like the F-35.
They do, which is why you're seeing significant government investment, like $1 billion, to try and build more secure supply chains.
And the energy transition adds another layer of urgency.
Definitely. The IEA warns we need maybe 4 times the mineral supply by 2040 for net zero goals. But current trends suggest we might only double supply. That could mean a 50% shortfall in critical minerals like rare earths.
We also have to talk about the environmental cost. It's not a clean business.
Far from it. The mining often involves radioactive waste thorium, uranium, which can contaminate air and water. The processing is chemically intensive and generates enormous amounts of toxic waste or sludge.
I saw a figure like 2,000 tons of toxic waste for every ton of rare earths produced.
That's a commonly cited figure, yes. And the situation in Myanmar, with deforestation and health problems linked to the mines, is a stark reminder of the potential damage when regulations are weak.
And cleaner methods are still mostly R&D.
Things like microbial extraction, like DARPA's Emperor project, show promise, but they're likely years away from being scalable. Significant investment is needed there.
So putting it all together, that wind turbine using 500 kilos versus a phone using half a gram.
And the projection of needing maybe 10 million turbines globally by 2050. The demand is just staggering compared to current supply.
It really drives home that oil of the 21st century idea.
Yeah.
Small amounts, huge impact.
Absolutely. Crucial for clean energy, tech, defense. But the scarcity of economic deposits and China's dominance make it a major geopolitical flashpoint.
Okay, let's zoom in on the companies involved. Who are the main players in this $5.6 billion industry? It sounds like a mix of Chinese giants and Western challengers.
That's a good way to put it. On the Chinese side, you have the massive state-owned China Rare Earth Group. This was formed by merging several big state players like China Minmetals and Aluminum Corp.
And they control a lot of production.
A huge amount, maybe 120,000 tons a year, especially the medium and heavy rare earths from places like Jiangxi. They produce oxides, metals, magnets. The revenue isn't public, but they likely control about half of China's official production quota, backed by state subsidies.
Who else from China?
Xingye Resources Holding is another major one. They're interesting because they have a global footprint, stakes in MP Materials in the U.S.
Really?
Yeah, about 7.7%. Also stakes in Vietnam, rare earth count, and Greenland minerals. They mine in the Sichuan, but also process concentrates and make magnets. Revenue estimated around $1.5 billion. They're a key link, sort of bridging Chinese processing in Western mines.
Okay, now turning to the West. MP Materials in the U.S.
Right. They run Mountain Pass, producing that 43,000 tons, about 15% of global supply. They mine bastnasite, started their own separation in 2024, and they're building a magnet facility in Texas.
They've had a lot of investment, haven't they?
Huge investment, over $1.7 billion since 2010. They're definitely the U.S. flagship producer, getting support from the Department of Defense and energy grants.
And Linus Rare Earths from Australia?
Linus is crucial. They operate the Mount Weld mine in Australia and a big processing plant in Malaysia. Production around 18,000 tons. They focus on neodymium and praseodymium, the key magnet materials.
So they're the biggest producer outside China?
Yes, the largest fully integrated non-Chinese supplier. They're also planning facilities in the U.S., revenue around $500 million USD last year. Vital for Western diversification efforts.
What about new players? Brazil?
Serra Verde in Brazil just launched their Pela Ema project this year. They're mining ionic clays, targeting those valuable magnet rare earths like neodymium and dysprosium, aiming for 5,000 tons by 2026.
So pre-revenue now, but significant potential.
Exactly. It represents Brazil really entering the game as a potential alternative supplier, aiming to contribute significantly to their GDP.
Any others worth mentioning?
Neo Performance Materials, based in Canada, is important for magnets they supply automakers like BYD. In China, Baotou Steel Union is another major producer from Inner Mongolia, and in Australia, Iluka Resources is developing a project called Eneabba.
But the real bottleneck remains processing, right? China's dominance there.
Absolutely. Around 85–91% of global separation and refining happens in China. MP Materials and Linus provide a critical non-Chinese alternative, but together there's still maybe only 20% of the global capacity. It's a huge imbalance.
So the landscape is Chinese state giants with massive scale and government backing,
facing off against Western challengers like MP and Linus, who also have significant government support now, and then emerging players like Serra Verde, showing there's potential for new entrants, but cracking that processing dominance is key.
Which naturally leads us into the country-level competition. This is basically a geopolitical chessboard, isn't it?
It really is. Let's look at the key competitors and why they're involved.
Start with China. Massive reserves, dominant production, processing, magnets.
Right. 44 million tons reserves, 240,000 tons production, that 85–91% processing, 94% of permanent magnets. Their motivations are clear.
Yep.
Economic power, billions in exports.
Geopolitical leverage like the Japan ban or recent tech export controls.
Exactly. And also meeting huge domestic demand. Think of their own EV giants like BYD. They actually import rare earths from Myanmar to feed their industries.
What challenges do they face?
Increasing pressure on environmental regulations and dealing with illegal mining, which some estimate could be 10–20% of their actual output.
Okay, the United States. Smaller reserves, but significant production now.
Yes, 1.8 million tons reserves, 43,000 tons production. But imports still high, $170 million, mostly from China. Motivations are primarily national security, their DoD reliance.
Hence the $1 billion in supply chain funding.
Right, and energy transition goals. Biden's policies, Trump's before him. They all need vast amounts of these minerals for EVs and wind, plus pure geopolitics trying to counter China, showing interest in Greenland, or even potential resources in Ukraine.
Main challenge for the U.S.
Still that processing dependency, and the high cost of projects like Mountain Pass, which limits how quickly they can scale up non-Chinese supply chains.
What about Australia, key ally for the U.S. here?
Definitely. 5.7 million tons reserves, 18,000 tons production via Linus. Motivation is being that reliable, diversified supplier to the West. Their exports are significant, maybe $500 million.
And they're part of alliances.
Yes, the Mineral Security Partnership with the U.S. and others, they're getting DoD contracts to help build processing plants. The challenge is the capital needed billions required to expand processing capacity in Malaysia and potentially the U.S.
Vietnam, huge reserves, but low production.
Exactly, 22 million tons reserves, but currently most of it gets exported as raw ore to China. Their motivation is economic growth. They're seeking foreign investment, maybe $500 million, to develop the sector.
So they're trying to balance relationships.
It seems like it. Supplying China while also courting partnerships with U.S. and EU. Their big challenge is the lack of domestic processing capability.
And Brazil, the emerging player.
21 million tons reserves. Production starting out via Serra Verde, aiming for 5,000 tons soon. Motivation is to become a significant alternative supplier, particularly to the West, boosting their own economy. Challenges are mainly infrastructure development and navigating regulations.
Any other notable mentions?
Greenland has those reserves attracting U.S.-EU interest. But Arctic mining is incredibly expensive, maybe $500 million just to start. Ukraine has potential untapped resources, but the war obviously complicates everything. Russia and India have large reserves, but minimal production due to various policy and investment hurdles.
So the underlying reasons for all this competition seem to be?
Several things. Technological leadership REEs are critical for AI chips, 5G, advanced semiconductors. That market alone is heading towards $10 billion.
The energy transition, that massive projected increase in mineral demand for net zero.
Geopolitical power, China's current control is seen as a threat, prompting billions in counterinvestment from the US and EU, and of course the direct economic stakes in that growing $10.4 billion market.
And that imbalance is stark. China making $2–3 billion just from magnet exports.
While the US is spending $170 million importing them, highlighting the vulnerability.
So the stakes are incredibly high. It's not just mining rocks.
Not at all. It's about who controls the future of technology, clean energy, and national security. Right now, China has the dominant hand, but the challenges to that dominance are definitely mounting.
Okay, let's wrap up by looking specifically at those challenges and the future outlook. It's clearly not an easy path forward.
No, there are significant hurdles. First and foremost is the environmental damage we touched on.
The radioactive waste, the pollution, the toxic sludge.
Exactly. The situation in Myanmar with deforestation and health crises is a worst-case scenario. Proper environmental controls and cleanup are expensive, maybe $100–200 million per mine, which can deter investment in Western countries with stricter rules.
Then there's China's dominance itself as a challenge.
Right. That near monopoly in production, processing, and magnets gives them immense market power. Export quotas or tech bans like those announced in 2024 can cause price shocks, potentially adding thousands to EV costs, for example.
And scaling up Western production and processing isn't easy either.
It's tough. We mentioned the $1.7 billion cost for Mountain Pass. Permitting and regulations in the US and Europe can be slow. New projects in places like Greenland or Sweden face huge startup costs, maybe $500 million or more.
And finally, the potential for actual supply shortfalls.
Yeah, the IEA projection of a possible 50% gap by 2040 between needed supply, 1 million tons, and projected supply, maybe 500,000 tons, is worrying. Plus, illegal mining, especially linked to China's supply, complicates global efforts to responsible sourcing.
So given those challenges, what's the outlook? What's being done?
Well, the main push is diversification. The US and Australia, through government funding and initiatives like the MSP, are aiming to build up significant non-Chinese production capacity, maybe adding another 20,000 tons or so by 2030.
And new entrants like Brazil and potentially Vietnam could help?
They could. Brazil's 5,000 tons and whatever Vietnam manages could add another, say, 10% or more to non-Chinese supply eventually.
What about innovation? Cleaner methods, recycling?
That's key. Things like DARPA's Ember project and other research funded by the DOE aim for cleaner, more efficient extraction, may be becoming viable by 2030. Recycling e-waste is another big opportunity. There are potentially 100,000 tons of REEs locked up in old electronics and industrial waste.
Could recycling make a real dent?
It could potentially meet maybe 10% of demand, perhaps supplying 10,000 tons a year by 2030. It's scaled up. But building the infrastructure for collection and processing needs investment, maybe $200 million, though that's still less than opening new mines.
Alliances seem important too.
Very. Things like the US-Australia partnership, the EU's Critical Raw Materials Act, MAUUs like Nigeria, France, they all signal a move towards collaborative, more secure supply chains among allied nations. Investment in R&D could also unlock new sources, maybe those potential deposits in Kazakhstan.
And are there alternatives to rare earths being developed?
Yes. Research is ongoing into things like cobalt-free batteries, or developing powerful magnets that use less or no rare earths. The IEA suggests alternatives could potentially reduce REE demand by up to 20% in the long run, but that's still uncertain.
So it's a really delicate balance, isn't it?
It is. The race for rare earths requires balancing the urgent need for these materials with innovation and environmental sustainability to avoid a crippling supply crisis. The West is investing heavily now to diversify and innovate, which offers a chance to challenge China's dominance, but it's going to take time and sustained effort.
Okay, let's try and summarize the key takeaways from this deep dive.
Right, so rare earth elements. Absolutely essential for a huge growing market, $5.6 billion today, driving our tech, the energy transition, and defense.
But China holds a dominant position, particularly in processing, creating a global imbalance.
Which countries like the US, Australia, and Brazil are actively working to counter, pouring billions into diversifying the supply chain.
And the need is urgent, with potentially hundreds of thousands of tons needed just for EVs and wind turbines in the West by 2030.
But significant challenges remain: the environmental impact of mining and processing, price volatility influenced by China, and a potential long-term supply shortfall of maybe 50%.
So, as we said, this isn't just about minerals underground.
Not at all. It's fundamentally about who controls the pathways to future innovation, economic prosperity, and national security.
So, a final thought for you, the listener, to mull over.
How do we, as a society, strike that balance? The balance between pushing technological progress forward and managing the very real environmental and geopolitical costs of the materials that enable it? What role do you think innovation, maybe recycling, and definitely international cooperation will need to play to ensure we have a sustainable and secure supply of these absolutely critical elements going forward?
Thanks for listening to the Cognito Pod.